Okay, so last time we ended with a problem, a free variable problem. And I just want to kind of go over it again and make sure we know how to express a solution. And then I'll express like a way to always identify the free variable and where there are free variables even in just normal row echelon form. So first of all, can anyone kind of say what the free variable, which variable will be free? So there's 4 variables here, and here it is in reduced row echelon form. What do you think the free variable will be? Yeah, in this case, it would be the 3rd variable. Now, since you've hopefully been working on the homework, you may have an idea of when there will be free variables, like when it's in row echelon form or reduced row echelon form, when you can always tell there's free variables. So let's do this example, and then I'll come do a general algorithm or general way to see. So if this is our free variable, let's call it alpha. Let's solve for our other variables. So the first equation says that x plus 1/3 alpha is equal to 0. The second equation says that y plus 2/3 alpha is equal to 4/3. And the third equation says, let's say w is equal to 1. So what is the solution? It's just that. So solve for x and you get -1/3 alpha. Solve for y, you get 4/3 minus 2/3 alpha. The third variable is our free one, and the last coordinate is just 1. This is for all alpha in our free variable. So, so what does the free variable mean? Could someone explain what the free variable means? Like, what is the alpha? Yeah, it means all real numbers. So to express a solution, right, you can just choose any alpha you want. So for example, let's suppose alpha is 0. Then here's an example of a solution. 1, 4/3, 0, 1 is a solution. So there's infinitely many of solutions. And think of this as like a function of alpha. So plug in something for alpha, and then you get a solution. Yeah, z is just alpha. So whatever your third coordinate is, it can be whatever you want it to be, as long as the other coordinates are dependent on that position. Does that make sense? So the first and second line say that whatever x must be, it must be -1/3 of whatever z is. Sorry, this is really z, right? And the second line says whatever y is, it must be 4/3 minus 2/3 of whatever z is. And z could be anything. So you can think of z as independent, right? And then x and y are dependent on z. And then w is just 1. It doesn't matter what z is. So, for another example, maybe 3 would be another nice one. So alpha equals 3 would be -1, whatever 4/3 minus 2 is. 3, 1 is a solution. Right, there are a lot more, but that's just an example. Okay, so any questions on that, on this one? Okay, so here's one that we didn't talk about last time. What if you have a scenario like this? Can someone say like what's the weird part of this system? If you look at this, like what's weird about it? What makes you scratch your head with this system? Yeah, this thing right here, right? So it's actually, it can be, yeah, what do you think the first, so the first X variable, what is it? When we express a solution, it's actually, so it's not 0, but it's actually anything. So let's think about let's write this in a as a system. So this is y equals 1, z equals 1, and w equals 1. But the idea is, what dimension is this? Three by 4, yeah. And the big part is that there's 4 variables, right? However, there is no condition on x, right? It's not x. This is not x equals 0. That would be a specific thing you need to say. But since there's no condition on x, then x can be anything, right? Plug in anything for x. Are these things true? Yes, they are true. Exactly, yeah. You can fit any number you want in this position because the 0 just cancels it out. So in fact, this is a free variable. It's weird because it's still part of the dimension, right? There's still 4 columns. I'm still talking about a 4 variable system. However, maybe think of it like this. There's always a 0x here, right? You're still plugging something in, but the idea is you can plug anything in. So since you can plug anything in, that's why we have a free variable and then 1, 2, 3. Does that make sense? So because those columns of zeros are there, I mean, in terms of calculations, yes, you can ignore it, but in terms of dimension, that's still something you need to consider when you express your solution. Okay, so it is kind of like a zeroed out row in terms of you can kind of ignore computations on it, but in terms of dimension, you still need to consider it because yes, it is still a variable. Okay, so here's the kind of general trick for free variables, and this is also true in row echelon. It doesn't have to be reduced, but this example is reduced. So a way you can check where free variables exist is it's entries that that are not leading ones. So leading ones exist in row echelon and in reduced row echelon. However, you can see where free variables exist in the entries that don't have, so this would be more useful for reduced row echelon, right? Because you would have entries that are not canceled out by reduced row echelon form. So for example, the second variable doesn't have a leading one as in a row, right? You know, it would have been here if it had a leading one. Same thing with the fourth variable, right? It has entries that are not leading. And what is this? The sixth variable has entries that are not leading. So this is a good way. So that's why a reduced row echelon form is so nice, that you can identify where free variables are just based on if they have entries. So kind of the main idea with leading ones don't need to be free or are not free, and then the entries that are not leading are free variables. So can someone say like what the solution would be? Like what would be the first coordinate? What would your x be? So free meaning, as we talked about here, so it can be anything. The variable that can be anything. The variable that can be anything. So the claim is that, free variables exist when in reduced row echelon form where the entries are not leading. So notice when you put something in reduced row echelon form, you always have these zeros above and below the leading ones, right? But there might be entries that are not leading, meaning the first entry in the row, the first non-zero entry in the row. These are leading. So these are leading. So every other entry is not leading because these are zeroed out just by nature of doing the Gaussian elimination, and then there might be some that are zeroed out or that are not zeroed out. So, for example, the second variable, right? This one cannot be eliminated. Same thing with this fourth variable. These ones cannot be eliminated, and these ones cannot be eliminated. So, sorry, it's getting a little messy. So, these three are free variables. So, can someone express what x1 would be? Your first entry. Maybe we can even just write the equation out. So it's x1 plus alpha, a free variable, plus beta, because it's a different variable, we need a different letter, and then plus gamma is equal to 1. So that means that x1 is equal to 1 minus alpha minus beta minus gamma. So based on that, can someone say what x2 would be? Or not x2. Yeah, well, x2 is the free one, right? And then what's x3? So the second equation, you can give an expression for x3. So what do you think it would be? Yes, first of all, the second equation just says x3 plus beta is equal to 1, right? So x3 would be 1 minus beta. Good. x4 is a free variable, right? So that's beta. And then what's x5? Why is x2 just alpha? Because that's the free one. So free variables are, it's whatever x2 is. Yeah, x5 is 1 minus gamma, where x6 is gamma. So this is just a trick to easily identify where free variables are. You just look at all columns that do not have leading ones when it's in reduced row echelon form. So leading ones are not free. And then for all other entries that don't have leading ones, then they are free. That are not leading ones are free. So that's it. It's 1 minus alpha minus beta minus gamma. That's what the first row says. The second variable is the free one. That's alpha. Third equation says x3 plus beta is equal to 1. So 1 minus beta. x4 is the free variable, or is a free variable. x5 is 1 minus gamma, where gamma is the free variable. So again, just to reiterate, non-leading ones are free variables. So it might be helpful just to have that kind of general rule. I mean, you could figure it out without having this kind of general scheme, but yeah, so any questions on that? So this might help for solving maybe some more complicated ones. So this is why reduced row echelon form is very nice, because it's very easy, you know, I shouldn't say easy, but it's easier to express a solution. Row echelon was nice, but you still have to do some work, maybe figure out free variables. But reduced row echelon form kind of gives you a clear way of expressing it. Okay, so that stuff. So 1.2, I believe, is due Wednesday. So now we'll move on to 1.3 stuff. I do have homework up here for 1.3. It's probably won't be due for a while because I like to spend a bit more time on 1.3. But this, yeah, it does kind of look weird. But if you just replace these with like X or Y, Z, and then whatever other letter you like, maybe it's just the Greek letters that can get confusing. But I mean, if you like just using Y, W, but when you get to more than 4, yeah, that's what any variable is, just a placeholder for whatever. Yeah, so if you don't like alpha, beta, as long as you explain what they are, right, then you can make whatever symbol you want. You can make triangle, square, and star if you really wanted to, as long as you explain what they are. Homework 2, I believe, is on Blackboard. I also have it on Discord. And yeah, Wednesday, like 11:59. But if you need more time, that's fine. It's just make sure you don't rush through it, but really kind of absorb and understand the material. All right. On the very bottom row, could you make the other variable the gamma? Yeah, you can always kind of flip around which. Oh, well, actually, in this case, since the first equation is dependent on gamma, I mean, you could, but it might be harder to express it, right? If you made this one the gamma, then you might want to express this differently. Essentially, you'd be kind of doing a column swap, but I think it's easy. I mean, yeah, you can. Solutions, yeah, it's all on here. Solutions to the first one. Yeah, there are always like different ways to express. I just think this is maybe the easiest one. I think if you make the fifth variable free, it might be a little bit harder, just because you do have to think about how it affects the first equation. Okay, so the idea of a homogeneous system is something that was talked about in 1.2. I like kind of easing it into 1.3 because I like it. All right, so what is homogeneous system? It's any system where you have some linear equation and it's equal to 0, then all other ones are also equal to 0. So essentially all the equations in your system are equal to 0. This is what makes it homogeneous. So it's the same homogeneous. They're all equal to the same thing, and it's equal to 0. So all equations in the linear system equal 0 is called a homogeneous system. So can someone say what's nice about homogeneous systems? This might look familiar. Yeah.
Wouldn't it be that they would always just, the solution will always just be zero?
Almost right. Zero is always a solution, but it may not be the only solution.
Mm.
But you're right. Homogeneous systems are nice. First of all, because they're always consistent. And because zero is always a solution. Is always a solution. Does everyone see why zeros is always a solution? Right, plug in zero to everything, and you're always going to get zero, right? So that is always a solution. But it's important to note that zero may not be the only solution. Can someone give me an example of a two-variable case where that's true? And maybe you've thought about this in the homework. So 0, 0 is a solution. Is there an example where you can have A, B, C, D that makes it not just 0, 0, but maybe more than 0, 0? What are those X and Y? 2, -2, 5, -5? So, I mean, what line are you talking about, right? Are those points on a line? Okay, yeah, when A equals B and C equals D, that is a case. When A equals B and C equals D, there are more solutions. Why? Because if you see that, AX plus BY, oh, I'm not C equals D and A equals B. When A equals C and C equals D, I think you meant, right? And then AX plus BY. So, right, they're the same line. So that's an example of homogeneous system that has more than just 0, 0 as the solution. Now, if you look in the homework solutions, it's actually more general than just this, but you might figure out, I would kind of prefer you to kind of think about it first before looking right at the homework, but it turns out that, oh, yes, then B equals D. It turns out that this is the condition. AD minus BC is equal to 0. Then they're the same lines. So in the homework solution, that's there. Somewhere. We'll look through that. I think it's one of these. Yeah, so kind of figure out that for yourself. Like, is there more than just A equals C and B equals D? It turns out that if you just have AD minus, so, you could just say AD is equal to BC. The products are the same. So product of the first times the second of the Y, that product is the same, then they will be the same line. So this is to say that homogeneous systems have 0, 0 always as a solution, but there could be more. It's nice when it's the only solution, but there are examples when it's more than just 0, 0. And we'll talk about this even more later in the course. But it's just kind of a little intro to that. Okay, any questions on homogeneous systems? And we see why 0, 0 is always a solution, but maybe not the only one. Okay, so let's see why homogeneous systems.
So would there be another case where there would be more than one solution instead of just like 0, 0?
Yeah,
Yeah.
that's this case here.
Okay.
That's infinite solutions, right?
Mhm.
So remember that the only times you have a solution is that there's no solution, there's one solution, or there's infinite solutions. We write there can't be any. Yeah, can someone say why there can't be like 2 solutions? Like if you have a if you have 2 points that are a solution, well, why can't there be 2 intersections? That would be the implication, right? If there were 2, right? Because, well, there's only one line that passes through these 2 points, right? There's only one line that passes through these 2 points. So if there's more than one solution, it has to be infinite immediately. So that means that this thing is not a line. So that's a way to see that in like 2 variables. And that's the same idea for higher variables. That's the only possibilities is 0 solutions in the case of the parallel. 1 solution where they intersect, or infinite solution where they are the same line, or maybe 2 planes maybe intersect at a line, or any higher dimensional equivalent. So yeah, there's only 0, 1, or infinite solutions. Okay, so let's think about homogeneous systems as matrices and why those are nice. So let's say we have like A, B, 0, C, D, 0. Okay, so let's think about row operations on homogeneous systems. Can someone say what happens to the column of zeros when you do row operations? Not column operations, but row operations. Think about row operations and how it might affect. Right, nothing happens. So think about the first type, like row I swap row J. Well, they're both 0 in the last column. So nothing changes. What's the other type? You can multiply a row by a constant, but what happens when you multiply 0 by a constant? Nothing. And the last one. Well, if they're all 0, well, first of all, row is the position of, so in the last column, row the ith row in that column is 0, and the plus alpha times, well, the jth row in that column is also 0, so it's 0. So nothing changes. There does not exist a row operation that changes the last column in a homogeneous system. Does that make sense? So because they're all zeros, row operations don't do anything because every operation involves some multiple of an entry in that respective column. But if all entries are 0, there's nothing to do. Oh, the first one. So the first type of operation we have was swapping 2 rows. So if you swap these 2 entries, for example, well, both entries are 0. So it's like you're not doing anything in that column. So the other stuff changes, right? This stuff does change when you do row operations. But the idea is that the entries in a column full of zeros will never change. So this is true for all zeroed columns. In a column full of zeros, row operations will never change that column. So why is this so nice is that, well, if that's true, then it might be easier just to write it like this, right? Do I have to write out that augment 0, 0 every single time? Well, not really, because row operations don't change that. So when talking about homogeneous systems, maybe matrices, so the matrix without an augment is an object worth considering. So for example, it can be the linear system of a homogeneous system. It can represent the linear system of a homogeneous system. So when we talk about stuff on 1.3, we're talking about matrices as if they were their own types of things, like their own types of objects. So can we add these things together? Can we multiply these things together? Can we square them, square root them? All these things we consider with numbers and even with functions, maybe we can say the same thing about matrices. So this is what we're talking about when we talk about matrix algebra. So let's just remind ourselves what algebra is, like, that we are more accustomed to. Algebra of real numbers. So a lot of the same terminology will be used with real numbers, and a lot of the operations may look similar, but some of them might be a lot different. Like, for example, multiplying 2 matrices together is going to look a lot different than multiplying 2 numbers together. So, so first, let's just kind of understand what we mean by algebra of just numbers, and then see how matrix, when we go into the matrix world, it's a little bit different than working with numbers. So there are 2 main operations of real numbers, right? There's addition and there's multiplication. So can someone remind me what, when I say addition is commutative, what do I mean? Yeah, so I have like a plus b. What does that equal to? So I'm talking about addition, right? Yeah, plus, not y. A plus b is equal to b plus a. Good. Okay, when I say addition is associative, what does that one mean? You remember what associative means? Remember, associative works with like parentheses. That helps. Like, it's about grouping, addition. So subtraction is a bit, that's different. Yeah. So addition, right? You can move around parentheses. Why am I using different numbers? Right. So if I have a plus b plus c, you can group either the last two or the first two, and because it's commutative, you can even group the last and the third. Just the question is subtraction associative? Well, first of all, is subtraction commutative? Is not good commutative. Why? A minus b, that's not equal to b minus a, right? Yeah, it does change. Is subtraction associative? Also no, yeah. If a minus b minus c, and you have a minus b minus c, well, what does the first one give you? Is a minus b plus c, and this one gives you a minus b minus c. That's why we don't really think about subtraction when we talk about the nice things about addition, right? Really, when we think about subtraction, we think about something about inverses, right? But so first, to talk about inverse, we need to talk about an identity, right? Then remember the identity element of addition is? First of all, what does identity element mean? Yeah, it's the number where if you add it, it doesn't change. So a plus 0 is a, and it doesn't matter where you add it, you always get, it does not change the number. So that's what I mean. What I mean by identity is the element that you add that doesn't change. So, and remember what inverse means? Yeah, it's the element that you add such that you get identity back. So it's the element that you add to get the identity back. So the inverse of a is negative a, and the inverse of negative a is positive a. Okay, so are we comfortable with those? So we might throw these terms around more. So let's do enough of that, and let's talk about multiplication. Okay. Oh, yeah, we don't need to talk about subtraction with this. Oh yeah, so subtraction, you might want to think just of adding the additive inverse. So that's when we think of subtraction, is now it's just adding the negative inverse or adding the inverse. Okay, is multiplication commutative? Yes. A times b is in fact equal to b times a. Now, just a little spoiler, this won't be true for matrix multiplication. Whenever we define that, it may not even be this class, the next class. But that's kind of the big thing to kind of drill into your mind, that this is not true for matrix multiplication. Is multiplication associative? Yes. A times b times c is certainly equal to a times b times c. What's the identity element of multiplication? What do you multiply a number so it doesn't change? 1. 1 times a is equal to a, and a times 1 is equal to a. And what's the inverse? What do you multiply a by to get 1? 1 over a, yeah. Is there a number where that doesn't have an inverse? Yeah, 0 does not have an inverse. Now, just a little spoiler also, there are many matrices with no inverse. But we haven't even talked about what multiplication is. But so something with the identity, and in matrix land, there's more than just the 0 matrix that, or whatever 0 means, that has no inverse. Okay, so that's just to get some terms out of the way. So now let's talk about actually what these things mean. So let's start with matrix addition, because that's an easier one to understand. One caveat with this, but we'll define it. All right, so adding two matrices. So first of all, I just want to remind notation. I don't remember what, if A is a matrix, what does A, little ai, comma, j represent? Remember what that notation means? We haven't used it in a couple of classes. Yeah, this is the entry in the ith row. If it's I, it's the ith row, and then j is the jth column. So when we talk about, when we will talk about operations on matrices, we're mostly going to be talking about what are the entries in the matrix. So if I want to talk about what is, so the entries in C, which is equal to A plus B, the ijth entry in C will be defined to be the aijth entry, the ijth entry in A plus the ij entry in B. And that's how we're defining matrix addition. So for example, let's just do an easy one. So here are two matrices. So what we're defining as matrix addition is that, well, let's look at the 1, 1 entry. Yeah, the lowercase just is for the element. The capital is for the matrix. So like if this would be A, this is B, and this is C. And then entries will be lowercase in general. I mean, there are different notations, but this is what I like. So remember, these are entries. Yeah, answer is 6. So for the C11 entry, you take A11 plus B11. So that's 1 plus 5 is equal to 6. Okay, what would this entry be? So it's C21 is equal to A21 plus B21. Yeah, you asked the good question. What if they have different dimensions? Etc. So this one would be 8, and this one would be 12. So that's the caveat to this. What if A and B have different dimensions? You just can't do it. Cannot add two matrices at different dimensions. And think about it as the definition. Right, there might be entries that are not accounted for, right? Let's just do an example. 1, 2, 3, 4. You just can't, yeah. So we're defining matrix addition only on matrices of same dimension. Right, so there would be entries here, like no matter what you make up a dimension, there's going to be a position that is not accounted for or not or missing. But it's not true for other operations. So for multiplication, you can in fact multiply different dimension matrices. There's a specific condition on what the different dimensions should be, but it's only true for addition that they must be the same dimension. For multiplication, there are some dimensions where you can't even multiply, like even if they're the same dimension. So this is why multiplication is so kind of more confusing than addition. So we're going to spend a lot of time on like what multiplication even means for matrices. But addition, they have to be the same. All right. Does that cover that? Is matrix addition commutative? Yes, it is. So let's think about, so C is equal to A plus B, right? We defined every entry to be just coordinate-wise addition. Now, what is this addition here? What type of addition is that? Is that matrix addition? What am I adding there? Yeah, those are just numbers, right? These are just normal numbers. That's why it's so helpful to define. So this is the weird addition that we don't know yet, right? And this is what we're defining. We're defining the result of each entry just to be normal addition. So we do know that number addition is commutative. So that can be swapped. Now, this is an expression for whatever B plus A would be, right? This is how you define how to add A plus B. But if they were the other way around, that would be expression how to add B plus A. So that proves that matrix addition is commutative because the entries are the same. Oh, well, maybe I should have said what, I mean, maybe a definition that doesn't really need to be said, but two matrices are equal if all entries are equal. So i.e. like Aij is equal to Bij for all I and j. So that's what it means to be equal. So since you can flip around the order of addition for normal addition, and then this is an expression for how you add B plus A, that makes A plus B equal to B plus A. Okay, let's do the same thing for associativity. Okay, so let's express the entries in A plus B plus C, and let's express the entries in A plus B plus C. So first of all, what would the entries in B plus C look like? Can someone say, just based on our definition? So nothing complicated here. So, right, you take, what is the ijth coordinate of B plus C? Yeah, just Bij plus Cij. So now we're taking this and adding A to it. So what you would add here is Aij. So now what this in aggregate is, this is the addition of the two matrices A plus the B plus C. Is that okay? So in the parentheses is the result of adding B plus C first. And then how do you add these two matrices together? Now these are two. Do exactly as we described. So that, right, this is the ijth coordinate of B plus C. So now in this expression here, what type of addition is it? So these are just numbers, right? So then we know that's associative. Or we know normal addition is associative. So why don't we just group the first two together? But now, what expression is this? So what are entries in this matrix? So first of all, let's say, what are entries in, these are entries of what matrix, I should say? A plus B, yeah. And Cij is entries of what matrix? C. So shown that A plus B plus C is equal to A plus B plus C. So matrix addition is associative. All right, any questions on that? So kind of get used to the IJ stuff because we'll be using it more. Addition, there's not too much to do. We'll get to multiplication. It's going to get a little bit more kind of hard to keep track. So kind of get used to it soon. All right. What do you think the additive identity of matrix addition is? The zero matrix, yeah. So what is the zero matrix? The matrix full of zeros. Now, one thing that should be said is that in the appropriate dimension, right? Right? The zero matrix may look different in different dimensions. So for example, A, B, C, D plus 0, 0, 0, 0. We haven't talked about multiplication yet, but it turns out that, yes, and we'll prove it, that multiplication is associative, but it turns out it's not commutative. Yeah, so if you add a matrix full of zeros, nothing changes. And how about inverse? I mean, also this is true. What do you think the inverse of a matrix is? Additive inverse. So what do you add? Yeah, so you add the negative. And how do you define the negative of a matrix? It's the matrix where all entries are negative. That's 0. So the additive inverse, so negative A is defined as, well, what are the entries in negative A? So you could maybe say negative Aij is equal to negative Aij. So the entries in negative A are just the negative of each entry. Okay, questions on that? Yeah, and addition is pretty straightforward, but multiplication isn't. So I'm going to talk more about that. But I just want to make sure, is everything okay with addition? Any questions? Okay, so before we go right to multiplication, I'm going to take a little detour into functions. So this may or may not be your first time seeing functions in 2 variables. So, but we'll kind of ease up to it. So it turns out that matrix multiplication is pretty much function composition. So this is kind of the motivation of talking about functions right now. And moreover, is that linear functions on a plane, and we know a couple, can be represented as a matrix. So we're kind of going away from the idea that linear systems are matrices, but there are other uses for matrices. One such use is talking about functions in more than one variable. And you can even think about the linear functions in one variable are pretty much matrices as well. So let's think about some linear functions that we do know. We may not know whether they're called linear, but functions on the plane. So here's a function on the plane, a reflection on the x-axis. So here's the plane, and I have a coordinate x, y, and I want to reflect it over the x-axis. Can anyone say what the result is? Where does x, y go? What point does it go to? X negative y, yeah. So if you just look at the picture, the y is the coordinate that gets negated. So we can express this as it's a function x, y that goes to x negative y. Okay, how about y-axis reflection? That one is negative xy. So it's a function f that goes to negative xy. And you remember this one, the x equals y reflection. So a hint is that this was used in talking about inverses. So let's look at the picture first, then you might want to change your answer. There's no negatives, right? This is still in the upper right quadrant. So yeah, it's yx. So if you remember, when you calculate the inverse of a function, you flip the x and y. It's akin to if you reflect a function over the y equals x axis, you actually flip the variables x and y. So if this x coordinate becomes this y coordinate becomes this x coordinate. Yeah, so that is f of xy is yx. Okay, let's do, I remember this one, origin reflect. Another way of saying this is 180 degrees rotation. Yes, that one is negative x, negative y. So it's a function that takes x, y, and brings it over to negative x, negative y. And one that maybe some of you know. How about 90-degree rotation? Let's do counterclockwise. And if you don't know, let's do an example. Close, it's not negative xy, that's a y-axis reflection. We can do a specific example, then you can maybe figure out what it should be. And I remember the pi over 6 point on the unit circle. Yeah, what is it? Might be hard to type out. So the first one was square root over 3 over 2, and then 1/2. Now, let's rotate this 90 degrees. Where does it go? Pi over 6 plus pi over 2. What is that? Correct, it is negative yx. Yeah, this goes to 2 pi over 3. And this point here is negative 1/2 and radical 3 over 2. And we can see in this particular instance is negative yx. Okay, questions on that? So other ones that exist, X dilations. Won't draw a picture for it because it's not as nice. Probably need like a shape to understand it. Y dilation. So any multiple of X, it's like a stretch, or any multiple of Y, which is like a stretch or a shrink. So maybe we've seen these before. So now I claim that all of these functions, they can be represented as matrices. So that's kind of cool about matrix algebra is that all these very common functions that we do know already, most of these we may know, these can be represented as actual matrices. So here's where we're going to define operation matrix. First, you can do for 2 variables, but it works in higher dimensions as well. Okay, so let's say we have f of xy, and it's going to equal something. So one of the things that we've talked about, and then we'll kind of figure out what the matrices all look like. Okay, so For a two variable, it's going to be a 2 by 2 matrix. And the rows will represent the coordinate. So how is the first coordinate changing versus how is the second coordinate changing? And what are the columns going to represent? It's going to be it's the contribution, call it the contribution of x, contribution of first variable is going to be the first column, and the contribution of the second variable. And I'll explain what contribution means. Is the second column. So if you have a matrix A, B, C, D that inputs X, Y, we're going to say it outputs. So in the first coordinate, it's going to be A times the first variable, and then it's going to be plus B times the second variable. In the second coordinate, so that's what we look at the second row. It's going to be C times the first variable plus D times the second variable. This is how we're just defining a matrix as a function, as a linear function. Notice it's linear because these things look like lines, right? So it's linear on both X and Y. Okay, so let's think about what these matrices look like for the various functions that we described. But first of all, anybody have questions on what all that means? So there's 4 components going on in a linear function of 2 variables. I think that's 2 squared. It's how the first coordinate changing and how is the second coordinate changing. And there's 2 things that contribute to the change with each variable. How much weight is assigned to the first variable and how much weight is assigned to the second variable. So that's where you can think of the A, B, C, D as weights of each variable. So it's a certain amount of stretching and shrinking or reflecting in each variable. So it's dot product comes from matrices. So if you really want to, we'll actually define dot product a lot later in the course, but this will look extremely similar to dot product because it is dot product. So let's do an x-axis reflection. So remember, this was f of xy was equal to x negative y. So let's think about the matrix. So let's look at x negative y. What weight do we assign to the x variable? Or how much x is contributing to the function? Just say how many x's are there in the first coordinate? 1. Yeah, there's 1 of them. How many y's are there in the first coordinate? In the first coordinate. Yeah, there's nothing, no y's there. So now that takes care of the first coordinate. How many x's are there in the first coordinate? 0. How many y's are there in the first coordinate? Well, there's negative there, so it's negative. So this matrix represents the action of x-axis reflection. So a lot of these reflections may look similar. Okay, can someone say this one? What's the first row going to read? -1. Yeah, there's -1 of x's. How many y's are there in the first coordinate? 0. How many x's in the second coordinate? 0. And then 1. 1y. Yeah, let's just do it for all of them. So what was f? What was x equals y? It was f of xy is equal to yx. So in the reflection over the x equals y, what's the first row going to read? Zero, 1. Yeah, there's no x's in the first coordinate. There is 1 in the y. And in the second coordinate, there's 1 in the x's and 0 y's. Origin reflection, that was f of xy is equal to -x, -y. We have, it's going to be -1, 0, 0, -1. And then for 90-degree rotation, so it's -yx, it would look like 0, -1, 1, 0. Okay, so we're pretty much out of time, but to get you started thinking about matrix multiplication, let's think about function composition. Okay, can someone remind me? We still have some time. What's the difference between these two things? F of g versus g of f. Let's just put this. Last thing, then we're done. Yeah, so in this case, it's first do g, then do f of the result. This one, this is exactly what you guys said. This is first do f, then do g of the result. All right, we're out of time, but here's an example. Sine of x composed with x squared is a lot different than x squared composed with sine. Right, this one would be sine of x squared, and this one would be sine of x squared. So between now and Wednesday, think about composing the various reflections that we talked about. So for example, what would be 90 degrees, then x reflect versus x reflect, then 90 degrees rotation. So try to figure out like what x, y goes to in each of these cases. Those are going to be 2 steps. All right, sorry for going a tiny bit over, but okay, we're done. So on Wednesday, we'll talk about matrix multiplication, how pretty much what we're doing here. And that'll give us a nice motivation to talk about what multiplication means. All right, I'm going to stop recording.